In the beginning, the universe was believed to have originated from an infinitely dense point of matter. This state underwent a massive explosion, what we call the Big Bang, which led to the formation of atoms, molecules, stars, and galaxies that we observe today. For decades, this has been the prevailing explanation among physicists. However, recent scientific discoveries are challenging this long-held view. New research suggests that the universe may not have a singular point of origin after all. Instead, it could be part of a vast cyclical process, a repeating loop of expansion and contraction that might go on forever. Renowned physicist Brian Cox has also voiced skepticism about the Big Bang theory, questioning the idea that something can emerge from nothing. His doubts add an intriguing twist to the ongoing scientific debate. Adding to this shift in understanding, the James Webb Space Telescope has provided data that calls into question the notion that the Big Bang marked the absolute beginning of the cosmos. This leads us to a profound question. If the Big Bang wasn't beginning, then what came before it? Join us as we embark on a journey into the origins of the universe, exploring the edge of scientific knowledge and diving into mysteries that redefine what we know about space, time, and existence itself. If you're passionate about uncovering the secrets of the cosmos, be sure to subscribe to our channel, like this video, share it with others, and turn on notifications to stay updated. Scientists have constructed a highly detailed understanding of the universe's early evolution through the Big Bang theory. According to this model, around 13.8 billion years ago, the universe was far smaller, hotter, and denser than it is today. In mere minutes, the building blocks of our world, basic elements, were forged. During this early phase, the entire observable universe may have been as small as a peach, with temperatures soaring above a quadrillion degrees. What's remarkable is how consistently this narrative aligns with observational evidence. From the faint afterglow of ancient electromagnetic radiation, cosmic microwave background, to the observed abundance of light elements like hydrogen and helium, everything appears to validate the predictions of the Big Bang theory. Yet, despite its explanatory power, the Big Bang model remains incomplete. A critical piece is missing, a definitive account of the very first moments of the universe. This gap exists largely because our current physical theories, namely general relativity and high-energy particle physics, are insufficient to describe conditions at such extreme scales. As we approach the moment of the supposed singularity, a state of infinite density, the mathematics breaks down, and our theories no longer provide meaningful answers. The singularity concept, while central to the traditional Big Bang theory, poses a paradox. It suggests that everything was compressed into a point of infinite density, a notion that defies physical understanding. To move forward, we must push the boundaries of modern physics. We need theories that not only extend beyond general relativity, but also unify it with quantum mechanics. One such candidate is string theory, which attempts to reconcile gravity with the other fundamental forces, especially under the extreme conditions of the early universe. String theory introduces a compelling idea known as the ekpyrotic universe, derived from the Greek word for conflagration or cosmic fire. This model proposes that what we perceive as the Big Bang may have been triggered by a preceding cosmic event, not the true beginning, but rather one phase in an eternal cycle. Building on this idea, scientists have proposed cyclic cosmology, a theory in which the universe undergoes endless cycles of birth, death, and rebirth. In this framework, the universe as we know it may be just one chapter in an infinite cosmic saga. The universe has fascinated humanity for millennia, and string theory offers a strong mathematical framework to support this fascination. Within the context of cyclic cosmology, the universe is seen as endlessly oscillating between vast expansions and catastrophic collapses, an eternal cycle extending infinitely into both the past and the future. This concept of a cyclic universe was put forward by the renowned physicist Roger Penrose, a Nobel Prize laureate. Penrose was struck by a surprising mathematical similarity between two seemingly opposite cosmic states. The universe's fiery, ultra-dense beginning, the Big Bang, and its far future state, cold, expanded, and nearly devoid of matter. According to his theory, when pushed to extreme limits, these two states become mathematically indistinguishable. Paradoxically, the complete absence of matter may be the very condition that leads to the creation of all matter in the universe. From this viewpoint, The Big Bang arises not from some external cause, but from what remains after everything, all matter, is swallowed by black holes and eventually evaporates into scattered photons in an empty void. In this scenario, the universe is reborn from a state that, while seemingly nothing, still constitutes a kind of physical reality, an empty universe poised for renewal. The core mystery lies in how this final, cold, empty state can be equivalent to the initial, dense, hot one. This equivalence is made possible by a sophisticated mathematical approach called conformal transformation, a geometric technique that alters scale but preserves shape. Penrose demonstrated that through this scale transformation, the spatial and temporal structures of both states align. Despite appearing vastly different in size, these two states are in essence the same. Under the extreme conditions of such cosmic phases, the notion of size becomes meaningless. In cyclic cosmology, events transition from an old, cold state to a new, hot one. The dense, energetic beginning of one cycle emerges from the faded remnants of the previous universe. However, this progression doesn't follow conventional time. At these extremes, both time and size lose their standard definitions, placing the cold and hot states on disconnected timelines. From an observer perspective, the empty state would appear to last forever within its own frame of time. This is where physics intersects with philosophy. Cosmology offers intricate and speculative explanations for how these cycles might operate. Yet even if Penrose's model gains empirical support, a deeper philosophical question remains. What is the origin of these cycles themselves? Why is there something rather than nothing? To explore this within the framework of physics, three possibilities emerge. There may be no physical explanation. The cycles simply exist without cause. There may be an infinite sequence of universes, where each universe's initial quantum state is somehow shaped by the one before it. There may be a single, repeating cycle, in which the end of the universe directly explains its own beginning. These options are scientifically appealing because they avoid relying on uncaused events and instead propose internally consistent physical mechanisms. Penrose, guided by his interpretation of quantum mechanics, leans toward the idea of an eternal sequence of cycles. In quantum mechanics, a system exists in multiple states simultaneously until it is observed, collapsing randomly into a definite state. Penrose suggests that similar quantum randomness could influence each cosmic cycle, giving rise to the diverse structures and outcomes we observe. Differences between cosmic cycles could offer exciting new opportunities for experimental physicists. They may even make it possible to detect faint imprints or anomalies in the leftover radiation from the Big Bang. What's your take on this? Share your thoughts in the comments. If you enjoyed the video, don't forget to like, subscribe, and share it to help us reach more curious minds.